let's start lecture number 3. Today we are going to talk about two additional operations, differential operations, in which the nabla operator is also present. And these are important operations because they appear in Maxwell's equations. And these are operations on vectors. So in summary, today's plan, we're going to talk about the divergence or the divergence operation on a vector, which gives a scalar function. The analogous operation that gives a vector is a curl operation on a vector. I'll talk briefly about some vector identities. Some are very easy to demonstrate, or others are more, the demonstration is more involved. Then we're going to talk about Gauss's theorem, which is a generalization of the divergence definition. Also Stokes' theorem, which is a generalization of the curl definition. And finally, an important theorem, which is Helmholtz's theorem, which gives what are the required information on a vector field to completely specify it on a domain. Okay. We start with the divergent operation, which is a differential operation on a vector which yields a scalar function. And this is very useful to detect field sources or sinks. By a field source, we talk about types of fields that have singularities, for instance, like the one shown here. For instance, electric charge creates around field of force, let's say, in which a test charge placed nearby will feel this force. For instance, it might be repelled from the region. And then we can picture these situations as having those field lines. And the field lines might appear to be coming out from a single point, like this one here, right? So it looks like, this type of field is a field that appears to be being originated on a point in space. Okay, we can give you a real. I forgot to open my notebook here. Let me find it again. Where's my notes here? For instance, a very real picture of this is when you talk about evaporating a metal on a surface. What people do is they make a vacuum chamber. They have a small amount of material, okay, and this material is a metal material. You want to evaporate on a surface like this. So what you do is you can heat it. You can put this on a type of holder that is heated. Then this thing evaporates radially in all directions, and part of it will be collected on this surface. So here you have a real source of diverging, material. You can even calculate the flux of material through a surface. Okay, you can show, for instance, that the flux density, let's say, obeys an inverse square law. so that the material deposited, the material that passes a sphere of radius r, is always constant. So here we have a real case of a diverging field. In this case, is the velocity field of the mass that is being evaporated, which has this property. Is a field that is diverging from somewhere. In the same way, you can have a sink, right? You can have a sink. I mean, fields might be converging to that point. For instance, we have a positive charge, have a source. Fields emanating from that will repel a positive charge. And you have a negative charge, for instance, you have a sink. Because if I place a test charge here, which is positive, it's going to be pulled toward the negative charge, which is on the center here. So this is the idea to detecting sources or sinks of fields. So the divergent, the operation divergence is used for that. So how do we define? Well, it's a differential operation. You surround the region of interest by a closed surface, okay? This surface encloses a differential volume V, delta V in fact. And by definition, you measure, you calculate the flux of the given vector field in which you are interested in determining the divergence. So you just calculate the flux of this vector outwards of the volume, right? So we have here we have a differential volume, we have a surface of a differential volume, we make that flux calculation, and you make a ratio by the volume, divided by the volume, in the limit that this volume is very small. So let's take a look at the dimension of this operation. So divergence of F, by definition, right, is this limiting process. Calculate the flux. So you want to make sure that something is coming out. So that's why you calculate the flux. If you have a positive flux, it means that you have divergence, you have a source. You have a negative flux, it means that the field lines are entering that region. So you have a negative divergence. That's the idea. I have to make some thing here with to avoid damaging my own notebook that I share with you guys. So let me make a copy of this guy here. Let me get it, number 3. Let me do some quick addition here, just a second. This number 3 here, let's duplicate it. And duplicate it, done, and then I will just rename this one here drafts. Let's say drafts. Let's call it drafts. So I use the draft so I can scratch on it without damaging the class notes that I shared with you guys. So and also I have my notes here. Let me put it on that side. Let me close this one. Okay. So that's the idea. So as you see, the definition of divergence, right? So the divergence of a field, by definition, is this limiting process as delta V goes to 0 of the flux of F across the surface, outwards flux, across the surface that surrounds the volume. Okay, let's say like this, divided by the volume. So let's take a look, first of all, the property of this operation. The result is going to be a scalar divided by scalar. So this is a scalar parameter, right? And in addition, the physical dimension of divergence of F can be inferred just looking at the definition. I mean, you see here, which is dimension of field times area, right? Dimension of F times area square of length divided by volume, which is cube of length, which is dimension of F, can drop the arrow, don't have to use it, per unit length, right? So it means divergence of F is a scalar parameter, dimension is dimension of F divided by length. So we think because we have a limiting process, this is going to be a kind of derivative that will involve somehow the components of the vector field, right? Now, from now on, to define those operations, either the divergence or the curl operation, we're going to use our generalized curvilinear system. We're going to draw it here. So let's see here. We have this system in which we draw, you can see here, I'm going to show you, we have the basis vector, cyclic sequence AU, AV, AW, right? And by definition, AU is orthogonal to the first coordinate surface, which is SU, which should be this one. SU is orthogonal to AU. So SU has two segments, right? Orthogonal to AU, which is the second direction, in which we have a length which is to the V, right? And the third dimension, the third segment, H3DW, right? So this is the SU surface. We have one surface in the front part of this curvilinear cube, let's say. And the back part is here, right? And also we have, so let me just erase those so we can. We have the intermediate surface, which is being shown here, right? Which passes through the center of the cube, of this curvilinear cube. Okay, right there. So the center is exactly at U0, V0, V0, and W0. So in going from the, for instance, I'm just going to talk about one of the surfaces, because understanding one of them, you just make cyclic permutations to understand the other ones, right? So you don't have to look at all the 6 faces. We're just going to make one calculation simple, then make cyclic permutations. It's going to be easy to determine all the components of the divergence very easily, okay? Well, let me just say that let's talk only on the first coordinate, U, okay? Just see, I mean, this surface, intermediate surface, right here, is at U equals to U0, right? So, in going from the back to the front, passing through the middle here, I change the coordinate, not the length, by du, okay? So the length that we produce is h1 du, okay? So from here to here, the changing coordinate is approximately du over 2. The changing coordinate here is approximately du over 2. So the total change is du, and the length, if you want it, is h1 du1 over 2, h1 du over 2, okay? So, for instance, this is the surface U equals to U0 plus du over 2, and this one is U equals U0 minus du over 2, okay? What we want to do is to calculate the flux outward the volume that is limited by this curvilinear, parallelepiped or this cube. So what we're going to do, we have to calculate the integral on this surface here, right? Then on the back surface, right? So these are the u equals constant. Then you have to calculate integral across the surface. The second surface is AV, is this one horizontal here. One face, right? And the other face, the lower face here. And finally, two additional integrals on the two faces W constant, which are those here. This is W constant, right? And this other one is the back surface W constant. So we have to make 6 integrals. But in fact, we just have to calculate 2 integrals. The ones across u equals a constant, okay? Because doing that, we calculate the other ones, just make a cyclic permutation. So we have the additional contributions, okay? So what we have this here is that given the vector field in the curvilinear system, just recall that it's going to have 3 components, AU, AV, AW, along AU, AV, AW. Each component is a function of 3 variables, U, V, and W, right? FU along AU, FV along AV, and FW along AW, okay? So the flux outward is the flux across the 6 faces. So what we're going to do is calculate only on the 2 faces, which are the faces u equals a constant, which are separated in here, okay? Right? So recall that you have to calculate those flux outwards, okay? That's what we have to do, right? What I'm going to do is to calculate. In fact, we have to compare how much flux is in this surface in the front here relative to the flux on the back surface there, right? That's what I have to do. What we're going to do is to calculate the flux in the intermediate surface, u equals u0, and determine the other ones on the front surface and on the back surface relative to the intermediate surface. Okay, let's call this flux across the central surface in the direction of increasing u as psi u0. Okay? So once calculated this flux, the flux across the front surface is going to be psi of a change of u0 from u0 to u0 plus du over 2, right? On the back surface, toward increasing u is going to be psi u0 minus du over 2, right? So let's do that calculation. So across the intermediate surface, psi, this subscript here means the flux corresponding to the u equals constant surface. U0 is on the central surface. It's going to be the area element, which is the dot product, right? You see that, let me just do that. The sigma dot f equals to the sigma u fu plus the sigma v fv plus the sigma w fw. Right now we are calculating this contribution here on 2 surfaces towards increasing u, okay? So that's what we have, this one here. So this is the area, the sigma u, right? Because these are the, segments that are orthogonal to AUs. which are the 2 and 3 segments. dV dW H2 H3, right? That's what it is. So this is the contribution across the central surface. So the flux across the central surface is given by this, it's given by this contribution here. So when I go to the front surface, the flux outward, right, is going to be Cu0 plus du over 2, which I'm going to use a Taylor approximator, right? Function from a single variable, f of u0 plus du over 2 is approximately f u0 plus the increment, which is du over 2, first derivative, right? Recall that this function is a function of 3 variables, so it's a partial derivative, the f du at the central parts. Okay? If I want to go to the back surface, I go to minus here, so it's going to be minus there. So that's what I'm doing here. The flux in the front or back surfaces is equal to the flux on the central surface plus or minus the correction to first order. So on the front surface, going outward is going along the AU direction. So this is the flux that goes to the exterior of the volume. On the back surface, on the other hand, I'm calculating the flux towards the increasing U, but that's to the inside of the volume. So I have to calculate minus this quantity, which is the flux outward. So to the back surface, I have to change the sign. So to calculate the flux outward for the U equals constant surface, I just put a plus in front of the front surface and a minus in front of the flux to the back surface. Okay? So have to subtract those, then you have the contribution of the U equals constant. Just recall that, we have, just recall that Cu of U0 equals to H2 H3 dV dW Fu, right? Calculate at the center. I'm not going to put the arguments to avoid big expressions here. And also we needed the derivative ddu of Cu, which is going to be, well, recall that H parameters may be functions of the coordinates, right? But V and W are, and U, V, and W are independent variables, right? I'm in the point in space have 3 coordinates which are independent. So when I calculate the ddu of H2 H3 dV dW Fu, I can remove from the derivative the independent parameters, which is V and W. So it's going to be dV dW ddu H2 H3 Fu. That's what it is. Okay? So that's what we have. Here is formula. And then the contributions of the U equals constant surfaces is going to be, as I mentioned in the previous screen, flux in the front surface, which is to the right, to the increasing U, minus flux on the back surface. So we have the outward flux. And if you do the calculation, right, the only thing that you have what is it? Right there. So if you subtract the terms, one is plus, the other is minus, it's going to be twice this term here. So that's what happens. I mean, the difference results in this term. And as I mentioned to you, right? So there's going to be a du here and a derivative. And this term goes out of the derivative, right? And you have the contribution of the u equals constant surface. So that's what we have as a result. The u equals constant gives a contribution, which is very interesting. There's a product of three differentials, du, dv, dw, and a derivative relative to u, in which you have the u components and the h parameters that are orthogonal, related to the orthogonal directions to u. So that's the contribution. If I calculate the other fluxes outward, you just make cyclic permutations, right? So it's very easy by doing cyclic permutations. You know, you go like this: u goes to v, v goes to w, w goes to 1, sorry, to u, 1 goes to 2, 2 goes to 3, and 3 goes to 1, and so on. Okay? So that's what we got. So to calculate the contributions of the v constant surfaces outward, it's going to be the same thing. I mean, this isn't changed, same factor. U goes to v, 2 goes to 3, 3 goes to 1, u goes to v, right? And also, if you want to go to the double constant surfaces, this isn't changed. V goes to W, 3 goes to 1, 1 goes to 2, V goes to W. So, I mean, the flux outwards is the sum of these three contributions, okay? So that's the numerator. Let's recall the definition, right? I mean, the divergence, by definition, we are calculating this part here, right? The numerator of the expression. Then we are going to find the differential volume, make the ratio, then make the limits. So here we are. When we do that, we make the sum of the contributions. Okay, so we're going to have this common term, and the sum of three derivatives. Each derivative contains the corresponding component, the matched component of the field, u, v, and w. And every time those appear, you have the orthogonal h parameters, right? So in fact, well, all you need to do is just to know one of these terms, because there are two additional ones that you make by cyclic permutation. Okay? So when you apply the definition, the denominator of the expression is the differential volume, which we showed last class, right? Which is the product of the three segments lengths. h1 du times h2 dv times h3 dw. And nice is that the terms that goes to 0 in the limit is this one, sorry. This is the one that goes to 0. When you make the ratio between these two terms here, this one divided by that, so we are going to cancel out this one, right? Then you have the final expression for the divergence in a generalized UVW coordinate system. Okay, as I mentioned before, is a derivative involving the components of the field. Well, because of the curvature of the coordinate systems, sometimes those parameters change with coordinates, and it's important. I mean, that is taken into account when you calculate the divergence. So, I mean, just recalling the age parameters in the different systems, because it's important to know the age parameters, to know the expressions in the three coordinate systems that we work on this course, right? In the XYZ system, all parameters are equals to 1. In the cylindrical system, you have 1R1. On the spherical system, you have 1R sine theta. Okay, so the simplest expression for the divergent is in rectangular coordinates. That's what you got, right? So it's a simple sum, matched sum of partial derivatives. The fx dx plus the fy. Oops, this is wrong here. Please fix that in the class notes. This is the f dy here, the fy dy. And the fz dz, right? The fx dx plus the fy dy plus the fz dz. Okay. In cylindrical, well, what we have, right? Remember that the definition has the products of the h's on the denominator, right? So in cylindrical, let's just write down here on the left, H1, H2, H3, which is the parameter that is in the denominator. In rectangular is 1, in cylindrical is R, spherical is R square sine theta. So we have to divide by R in the cylindrical system. So that's what we got. 1 over R, okay, H2 equals to R, H1 and H3 equals to 1. So H2 times FU, FR. Second component, 1 over R, H1, H3, right, equals to 1. And here is 1 over R, H1, H2 equals to R. So this R cancels out this one, okay? So we don't have that. That's why it's like this. So this is the expression in rectangular coordinates. Also, in cylindrical coordinates, let's see here, we have R squared sine theta in the denominator. Okay, maybe we should calculate also for the R theta phi. We have, for the first component, we have H2, H3. Okay, then you go to H3, H1. These are the components that appear inside of the derivative in each derivative of the divergent. Then you go to H1, H2. And here we have H1, H2, H3, which is R squared sine theta. So let's see here, H2, H3 is R squared sine theta, right? So I'm going to put here FU, so you can see here FV and FW is FR, F theta, and F phi. H3, H1 is going to be 1 times this, which is R sine theta, right? and H1, H2 is 1 times R. It's R here. So we're going to have the derivative of R2 sine theta FR ddr. Then we're going to have dd theta of R sine theta F theta. And you're going to have dd phi R F phi. Right? So recall that when you do that derivative, the sine theta here is going to come out. Right? The R is going to come out here. And the R is going to come out there. Okay? So that's why we have this final expression here. R squared sine theta cancels out with sine theta, which was here. Right? Have a cancellation. The second term, we have, just recalling here, the second term, we have R sine theta divided by R squared sine theta. So it's going to be 1 over R, right? Sine theta is back down in the denominator. And this sine theta doesn't come out because the derivative is relative to the theta variable, right? And finally, the last one, we're going to have this R coming out. Is going to cancel R squared. So we're going to have 1 over R sine theta. The F phi, the phi. Last term, right? So these are expressions. And we have a general expression. So just summarizing, if you want to know, I mean, if you want to go beyond the three systems that we are talking about, so you can say that divergence of a field, right, can be written as 1 over H1, H2, H3, ddu H2, H3, Fu, that's enough, plus cyclic permutations. So you don't have to write all of the terms. You're enough writing this one. Then you put plus cyclic permutations. If you want to make a calculation, just use the cyclic permutations, write down the expression, and perform the calculation. Okay. But what I'm saying is that the advantage of having a cyclic system of coordinates is this one. I mean, you can make cyclic permutations. Just knowing one term, you can determine the other ones. Some interesting situations here. For instance, I mean, that's just a qualitative, picture. A field that just passes, like this one, on a part of the space. They are not originated, they are not picking up, they are not getting strength as passing in a region in space. I mean, the strength is typically not being changed significantly. So the field is not increasing. I mean, the question is this: if the field increases along the direction, if a given field component has a dependence on the same coordinate of that component, it might have divergence. It might not have either, but I mean, it might have the divergence. If it doesn't depend on that coordinate, it's not going to have a divergence. So for instance, if I have a field which, let's say, the x component only depends on y and z, this field, I mean, this part of the field is not going to give, I mean, this component is not going to give any contribution to the divergence. The field might, I mean, if the field was just that one, I would assure you that this field doesn't have any divergence. On the other hand, if the field has one component, but also depends, the variation also depends on x, So you are going to have the derivative of fx relative to x, which is not 0. Then, it depending, in this case here, it would certainly have a divergence, right? This type of field. So that's, I mean, it's a field that picks up as it goes along the direction. If you write a field in a coordinate system with a single component, okay, you want to determine that if the field varies, if this single component of the field varies with this coordinate along the direction of the field. If that happens, it's going to have some divergence. Okay. There are some certain situations in which even if the field changes with that coordinate, might have zero divergence. Some special fields. We're going to look at those eventually. Okay. So I mean, this is one field that is not increasing, you know, as you go along the direction. So it would have a zero divergence. This one, as you see, has a line density that is larger in going along the direction of the field. So this would have some divergence. You see that there's some more flux on this surface here than in this one here. So the net flux around the volume in this particular part of the space would be positive. So you'd have a positive divergence. In this case here, you have a denser line density on the left entering the volume and have less field lines, let's say, coming out. So have a divergence which is negative. Okay. We are going to see, of course, that the E field has this property of having divergence, and the divergence of the E field, I mean, unless of a constant, is the charge density. So divergence of E field detects density of charge in space. Another important consideration that we have to look at, we'll talk about the divergence, but I mean, we see that there are derivatives, the derivative operations, and recall that the nabla operator has as components the derivative operations. So we see that we have combinations of components of the nabla operator and components of the field. They are mixed in such a way to give a scalar result. Okay. So notice that in the easiest, simplest case, in which you have a Cartesian field, rectangular coordinates, if you express the field in rectangular coordinates, okay, always recall that the components are functions of three variables for time independent fields, like this. And recall that the nabla operator has as components the derivative operators, right? What do we see here? If I make a simple dot product between nabla and f, what do we have? Recall that ax, ay, and az are constant versors. They do not depend on the coordinates. So in this case, the derivative acts directly on the components. So this is going to be ax dot ax, right? dfx dx plus ay dot ay dfy dy and so on, right? Plus as those dot products are all equal to 1, this is going to be exactly the divergence of f. So if we use just the rectangular coordinate system, you have divergence of f in fact equals to nabla dot f. Very simple, right? In fact, this doesn't have to depend on the coordinate system you use, because I mean, I don't know what f is. I'm saying that for a rectangular coordinate system, divergence is exactly equals to nabla dot f. Because this is valid for arbitrary f, this doesn't have to depend on the coordinate system. So this is a general relationship. This is valid for any coordinate system. Okay? If you prove that it's valid for one system, it has to be valid for any system. Right? That's intuitively logic. Of course, we have to demonstrate that with some mathematical, rigor. But that's what we would infer, because it cannot depend on the system. I mean, the vectors are there, the nabla operator and the vector field. I can change the coordinate system. I can do whatever it is. They're still the same vector and same operator. It doesn't change. Okay, so. This doesn't have to. This doesn't. I mean, the fact is this: the divergence of a field in any system is equals to nabla dot f. Now you have to be careful. On the other hand, how to calculate that, right? Let me show you an example. We have to be careful with curvilinear coordinates. Let's see this one. Let's calculate formally using the nabla operator. I mean, I'm going to calculate the divergence using the formal expression. Right? Let's pick one versor, A phi. Okay? So f is a phi equals 1 a phi. The divergence, by definition, is 1 r over r in this case. H2, H3, right? I'm sorry, H1, H3, which is 1 and 1, which appear here. So it's the derivative of H1 d d phi H1 times H3 times the second component of the field, which is 1, and the derivative is 0. So divergence of a phi equals to 0. I mean, using the formal expression that we just derived, right? Let's now calculate using the nabla operator. So we have to be careful, because versors in the cylindrical system might depend on the coordinates. Not might, they do depend on the coordinates. Not all of them, but two of them, right? So we have a nabla dot a phi. So we have the expression for nabla in cylindrical coordinates, dot product with a phi. So what we have to do is, I'm going to make the calculation here, right? Let's do it here. Nabla dot a phi equals to AR DDR plus a phi dd phi plus a phi over r, sorry, plus az ddz. Then I pick this vector here, make the dot product with a phi. Now we know that a phi, we just talked about that before. A phi only depends on the phi coordinates. Okay? So what I have to do here is, let me erase this thing here. It's going to be AR. So for the first one, we're going to have AR dot d a phi dr plus a phi over r dot d a phi. In fact, let's use the partial derivative, then we drop it, d a phi d phi, plus a z d a phi dz. We know that a phi only depends on the phi coordinates. So this is equals to 0, this is equals to 0, so we're going to have a phi over r dot product. Now, a phi depends only on the phi coordinates, so this is d total derivative of a phi dr, d phi, right? So I have to determine what is the phi, the a phi d phi. I can do it in two ways. I can do it analytically or geometrically. Let's do it analytically. We already did that before, I believe, right? So we have, you decompose the variable versor in a fixed basis, in a base that doesn't depend on coordinate, which is the Cartesian or rectangular coordinate. This is AR, this is A phi, right? So this is phi. So recall that AR and A phi are obtained by a rotation of phi radians relative to AX and Y. So this is phi as well. So we can say by the construction that A phi equals to cosine phi AY plus cosine pi over 2 plus phi, which is minus sine phi AX. So here I have the explicit dependence of A phi on the coordinate phi. So dA phi d phi equals to minus sine phi AY minus cosine phi AX. Which is minus cosine phi AX plus sine phi AY. So recall that AR by itself is cosine phi AX plus sine phi AY. So the derivative is equal to minus AR. That's what we have. Right? So dA phi, d phi is minus AR. So here we have a dot product of minus A phi over R dot product with AR, which equals to 0. Same results, right? So it works. I mean, for this example, it's going to work in any example, but it works. Let me just use this opportunity to show how to make this derivative geometrically, okay? Here we have XY plane. I'm going to show you, let me just center this thing here, something like this. So I'm going to draw the versors. I'm going to make the derivatives of the cylindrical versors. AR, A phi, and in blue here, in green, let's make it green, you have AX and AY. So it means that I make a small deviation of phi radians here, right? So this is for a given value of phi. So to calculate the derivative is to ask, if I make a small change in phi, differential change, what is the change in the versors AR and A phi? For instance, if I'm going to make a little exaggeration here, I'm going to make a little larger. Let me pick the new versor. AR is going to be like this. And A phi is going to be like that. After you make a small increment. So AR goes from here to there, so I have this change here. A phi goes from here to here, and we have this change. Okay? So these, in fact, I mean, I'm doing the two calculations together. So this is dAr, this is dA phi. Okay? For a small increment, d phi. Okay? So the segment, I mean this segment here has a length which is the radius of this circumference, which is 1, because we are talking about unit versors, unit vectors, right? So dAr equals to the length, which is 1 d phi, times the versor, which is tangent to the circumference, which is a phi. So here we got the first derivative. We are interested in dAr d phi equals to a phi, right? That's one of them. The other one is, what is the derivative of dA phi? Well, dA phi is has length that has the same length, right? This length here is 1 d phi in the direction of this versor here, but this versor is minus AR, which is directed along the radial direction. So it's 1 d phi times minus AR. So dA phi d phi equals to minus AR. So that's how you calculate those things geometrically. You know, vector derivative means difference, right? So have a vector, change the argument by a small amount, find the new vector, make the difference between those two vectors, and divide it by the change in the argument. Then you have the derivative of the vectors. Okay? Very well. Next operation that we want to talk about is the curl of a vector. Okay. And the curl gives this property. If a field has property of, you know, a rotational property, let's say. An example, for instance, is if you have, let's say, you have a river, right? You have water flowing in a river, running on a river. Near the margins of the river, the velocity field tangent, let's say, to the margin is very close to 0. And the velocity profile would have something like this, would increase like this, perhaps. I mean, the velocity increases as you depart from the margin, right? If you put a wheel here, it's very possible that this wheel will rotate like that, because we have more flux in here and less flux in there. So the velocity feels like this, right? Towards the margin. And if we put the wheel with, you know, with those, to measure the curl of this field, you're going to have something that rotates like this. So we have a rotational property of this velocity field. So that's what the rotation measures. So a curl operation is a vector, right? Because, you know, it rotates, so I have a component in this direction. If it rotates like this, I have a component in that direction. Depends to where you want to determine the components. So the curl gives a measure of the infinitesimal circulation of a field. In one way of determining is you go to a point, calculate the microcirculation of the field around that point, and see if there's a net result which is non-zero. Okay? So that's the first construction we have to determine the curl. If you want to determine the curl along the AI direction, okay, you align the surface in the the integration surface orthogonal to that direction. You calculate the circulation around the contour that encloses that surface, open surface, and then you have one property which is the circulation. In fact, I mean, notice that as we define this direction AI, the sense of of the path is going to be using the right hand rule. Imagine that you are holding the path with your hand, so you have this combination of directions. So by definition, the component of the rotational field, let's say, along AI, so is the projection of this vector, right? One of the components. Let's calculate one only. This component along AI, which is the projection, is a limiting process between circulation of the field and the path that encloses that surface, which is orthogonal to AI. Okay? That's the definition. Again, let's look at the dimension. Well, first of all, that's one component, so this is a vector field. So we would have to calculate three components of the field to build the curl of a vector, which is a field, which is a vector, right? What about the dimension of the curl? Well, dimension is, by definition, right? Length times dimension of field divided by area. So it's going to be L divided by L2 dimension of F. Again, is dimension of F divided by L. So it's field per unit length. So it's a kind of spatial derivative again, right? We're going to have some combination of derivatives of the components of the field. We are going to use the same procedure. We are going to use a curvilinear system. We are going to calculate only one component of the curl. Then we are going to make cyclic permutations. Okay, let's go, for instance, calculate the U component of the curl. So we're going to make this construction here. Have our area delta sigma U, which is orthogonal to AU, which is the product of two segments, H2dV and H3dW, right? Just to show you, these are AU in the cyclic orientation, AV and AW that way, right? So what we want to do is to calculate the circulation. Recall that the integration is made in such a way that the path, is run. You go around the path, having always the area on your left. Imagine an observer traveling along the path in which you want to calculate the circulation. So the area is always on the left. That's the consistent way of determining those things. So we're going to use that by convention. So that's how we are doing here, see? The area is always on the left of the observer that you can imagine traveling along the path. We are breaking the integral in 4 segments, C1, and going up, going in the positive sense of AW, and C3 going backwards, right? Going towards the negative sense. Again, and I have C2 and C4. C4 goes towards increasing AV, and C2 goes to the other direction, okay? What we're going to do is, again, we're going to calculate integrals along those intermediate segments here. IV, which is increasing V here, and IW, which is increasing W, right? So why do we do that? Because we calculate IV, then you calculate the integral on increasing V along the segment here. We calculate the integral along these other segments 4 here, along increasing V. Then I'm going to have to do integral along C4 minus integral along the increasing V on the segment here. Same thing here. We're going to have an integral along increasing U, and you'd have an integral along increasing U here, but we want the integral on the other direction, right? So what do? We calculate integrals, reference integrals. IV, which is increasing V, which passes in the middle of the right across the central point, and IW that goes to increasing W. Then you calculate those other 4 integrals relative to those 2, okay? So let's calculate, so what we're going to have? We're going to have the expression for the curl in the UVW system, just one single component, which is the U component. Then after we do that, we do the cyclic permutation, right? So that's what we have here. We have the 4 integrals, C1, C2, C3, and C4. And we have the central integral IV, which is this one here. IV is this one, right? Make it like that one, IV. So IV is just the second component of the field, which is FV, times the length from here to here, which is H2 dV. That's what IV is. The IV integral is this one. IW, on the other hand, is just what? The third component of the field, FW, times H3 dW. Let me just recall to you, right? Let's just make this. I mean, the DL, a general expression that we did before, right? Along U direction is this 1 du AU. Along the second direction is H2 dV AV. Along the third direction, H3 dW AW. F has 3 components again, right? FU AU plus FV AV plus FW AW. So if I want to calculate only on this segment here in which just U changes, V and W are constant, which is one of those segments, you're going to have FU H1 du. Second, I mean, if you are in the second segment in which U and W are constant, you have FV times H2 dV and so on. That's why we are having this, you know, IV and IW, right? So let me just erase this thing here, so we can do some additional thing here. Maybe I can erase this and that. So as we have IV, I can calculate, for instance, this integral here, in this path here, which I'm going to call, I mean, I2 is this integral going that direction, right? I'm going to call this minus I2. Okay? In fact, let me see, how did I do? It's minus I2. Yeah. Minus I2. Yeah. I'm saying that, yeah, that's exactly that. I mean, the integral, as according to my notation here, the integral in this oriented segment, oriented path, is called I1 plus I2 plus I3 plus I2 plus I3 plus I4. So this integral here is I2, right? So this one is minus I2, okay? This is I4. This is I1, right? And this one here is minus A3. So in fact, what I wanted to do is to calculate those integrals. So you see that, for instance, I1 equals to IW, which is the same type of integral, right? Plus a correction, which is related to a small change of the coordinates, which is the second one, by a small quantity. So I1 equals to approximately, to first order, equals to the IV, right? I'll just erase this thing here so you can see it better. Too much things here. Just make one at a time so you don't have a mess. So let's make only I1, okay? I1 equals to IW, right? IW plus the variation of IW on changing the second coordinate by half of the total change, right? DIW relative to what coordinates? Well, this one, which is the V coordinates, dV over 2, right? So let's go to this one here now. Minus I3 is the same thing. Minus I3 is equals to IW plus derivative times the change in V, but V now changed from here to here, changed by minus dV over 2. So it's minus dV over 2, right? Same thing, if I go here now, minus I2 equals to IV plus derivative of IV relative to this coordinate, which is the third one. And now here is increasing W, right? So the increase is the W over 2. And finally, I4, right? This is I4, this direction, equals to IV plus div dw. So the change from here to going there is a decrease of minus dw over 2. Right? So what we have to do is I1 minus I3 minus I2 plus I4. So this is going to be I1 plus I2 plus I3 plus I4. In this sum, okay, if I subtract this one from that one, I'm going to lose that one. So I'm going to have a sum. So this is going to be diw dv times dv, which is the difference between these two, plus I4 minus I2. So you cancel this. So you're going to be minus div dw. So that's what we have. So now, this is the result of the calculation. So the numerator of the definition, let's recall the definition here. The numerator is the circulation, which is the sum I1 plus I2 plus I3 plus I4. So the result, which is this one here, right? Right here. DIW dV times dV minus DIV dW. It's a cross derivatives. So just to conclude, I mean, well, what is IW, right? What is it? Let me erase those things here. So let's see here again, this diagram. Well, IW, I already did that here, right? IW, right? But it's not here. Let me see. Somewhere. No, it's not there. IW is third component of the field, FW, times H3 dW, right? That's IW. And IV is the second component, is FV H2 dV. So this DIW dV, but remember, the W goes out of the derivative because W is independent of V. Okay? So we have we had well, in fact, we have a factor that remains outside dV dW. So we have those two cross derivatives, right? And now this area delta sigma U is H2 H3 dV dW. Make the ratio, and the elements that go to 0 in the limit are those dV dW. This cancels out. So you're going to have the curl of U. We're going to denote by rotational curl of F in the U direction, which is this combination of derivative H2 H3 on the denominator, ddv, ddw, and you go ddv of the third combination, ddw of the second combination, right? That's the expression in the UVW system. And now you can determine in the other components just doing permutation, right? Recall here H2 H3, right? Then you go to H3 H1, first permutation, then you go to H1 H2. So this goes to W, this goes to 1, and U. So that's what we're going to have here. The other components. Just make 6 permutation. Right? So as I mentioned, but it's just enough to determine the U component because the other ones are determined by cyclic permutation. So if you want to make a expression for the curl, right? Curl of F in a UVW system is going to be the second component, which is 1 over H2 H3 ddv H3 FW minus ddw H2 FV plus cyclic permutations. Two additional ones, right? Don't keep doing forever permutations, just 2 additional ones. Make 1 permutation, then make another one. Well, I just forgot to put here the versor, AU, plus. So you make a cyclic permutation on everything that appears in the expression. AU becomes AV H2 becomes H3, H3 becomes H1, DDV goes to DDW, DDW goes to DDU, then you make cyclic permutation. But I mean, to know the curl, just enough to know this component of the vector. The other ones are cyclic permutation. For instance, in XYZ coordinate is the easiest expression, right? All edges are equals to 1, so this is Y, Z, Z, Y. So this is 1. So it's going to be DDY, can make it like this, AX, DF Z dy minus dFy dz plus cyclic permutations. Right? And so on. I mean, then you use the H parameters for the other systems. So these are the expressions. I will ask you to do those calculations because it has some H parameters that go out of the derivative and cancel out the denominator. So you have those combinations there. This is cylindrical coordinates, right? AR plus cyclic permutations. In spherical coordinates, you have one component plus cyclic permutations. Then you have that. Again, you just look at this expression you just showed. When this is nothing else, this is the x component of nabla. The x component of nabla is ay ddy cross product with az fz, which is a plus contribution, and the other one is az ddz cross product with ay fy. So this combination of cross products gives ay with az gives ax, y with z is plus, right? dfz dy minus, which is az with ay is minus ax, dfy dz. Right? So, and so on, right? ay dfx dz, I mean zx minus xz, ddx fz. xy now, dfy dx minus dfx dy. So you see again that, we are picking the components of nabla vector and making the cross product with f, and this is in rectangular coordinates is exactly equals to root of f. Right? So again, I mean, if it's true in one coordinate system, the vectors are there, it must be true in all the other systems. So this is a general rule in which the curl is simply the cross product between nabla and f, valid for any coordinate system. Okay. Here there's an example which is similar. I ask you to work it out. Make this example here, or I mean, I think in the assignment there's some examples for you to carry out. Just to show that root of AR equals to nabla cross AR. It's a similar example to the other one. Now in this case in cylindrical coordinates. Now there's a small typo here. This is AR. Okay. Root of AR. All right. reload. Very well. What's there here? Well, we have a second definition for the curl that's truly vectorial, because in this definition it just show that the circulation divided by the area in the limits is one component which is orthogonal to that surface element. That's the second definition. We are not going to prove it. It's just going to show you what it is, but just to show you the similarity with the definition for the divergent. So this second definition for the curl is the dual of that definition for the divergent. Okay. So one can show that the curl of f, it's shown in the ebook. You can take a look at the demonstration there. Okay. I mean, a truly vectorial definition, right? Simply is in fact defined in terms of volume integration. So it's very similar to the definition of the divergence. Is the limit as delta v goes to 0 of the surface integral of the cross product delta sigma cross f. The sigma is a surface element divided by the volume. So you see that this is a dual definition of the divergence, right? So just change the cross to the dot. They are very similar. The only thing you have to remember is that the sigma has to be on the left side. Otherwise you have the minus of the definition. So it's the sigma cross f. The divergence is the sigma dot f. But the rest is the same, right? Just change the cross to the dot. Then you have the divergence. So this is a very nice and elegant way of defining the curl. We're going to use in some demonstrations. You might use that property, that definition. I'm going to run a little quickly. We are already 1 hour and a half in this class on some properties of this. I'm going to show you one demonstration only. There's some interesting vector identities, okay, which you can use. Sometimes you need to use some chain rule, let's say, involving a vector field and a scalar field, and using the nabla operator. You see that nabla operator appears applied to on a function, have a gradient. On a vector, you can have a divergence or a curl. So nabla operator is always there, actuating on different types of fields, either scalar or vector fields. So in some situations, you have some identities like this one, right? What's the chain rule when you have the divergence of a scalar field times a vector? How do you expand that? In the same way, what's the chain rule when you have a curl of a function times a vector, right? How do you explain that? Let's make one of those. I'm going to make that notation in which repeated indices are equals to sum. So let's say that you have what is nabla of a function times a vector. How do you expand that, right? So here I'm going to express nabla as a sum, right? I equals 1 to 3. Whatever the system is, decomposed in 3 systems. Each of these components is a derivative relative to the ith length. I'm not gonna use that, but that's what you have to recall. So that's what you want to do the dot product of this times a vector field. Let's make a different index because we have 3 times 3 is 9 terms, right? So we have to make different indices here. AJ AJ, right? Then we have, well, it's not that, I have a function here, times the function, right? So I'm going to drop the sum symbol. I'm going to just represent this like this. It's implicit that we are summing over I equals 1 to 3 and j equals 1 to 3. So AI, so we don't have a lot of notation, a lot of symbols to play around. AI nabla I dot f, I forgot the f aj, right? Well, now I can do this. This is equals to AI dot. So this is a simple derivative operation, right? Nabla I of f aj, right? So here I can use the chain rule, the traditional chain rule that we know, right? AI dot. Well, derivative of this one times that, right? So I can put this outside, aj derivative. Notice that the dot is out here, right? Derivative of f plus f derivative of this vector component here. There's a simple chain rule that we intuitively know that already, right? So what we have here, this is, I can change the position here because this is the dot product. This is going to be aj dot ai nabla I applied to f plus f. This dot goes here, okay? ai nabla I dot, right? aj. So here we go. So this is a sum. Am I missing something here? Oh, wait. Yeah, I forgot I passed aj to the other side. Sorry. aj we put here, right? So when you remember that we have a sum from j equals 1 to 3, this is going to give a. Sum of I equals 1 to 3 is going to be nabla applied to f plus f. I summed from I equals 1 to 3 is nabla again, dot, right? J summed from 1 to 3 equals to A. So that's the chain rule that we have. The divergent of a function times a vector equals A dot product with the gradient of the function plus function times divergence of the A, right? So in the same way, you can do the cross product, the curl of FA. Now I have to go back to see what we cannot do in commutating the positions here of the elements here, because the vector product, the cross product, doesn't commute, right? So let's go back and review it. Let's make it now with the cross instead of the dot. So we're going to do now this thing here, right? Nabla dot FA. So that's what we have here, right? So far, I didn't do anything wrong here. Cross. Now, the first thing we do here, yeah, so far nothing wrong. Okay, this is correct. Now, at this moment, I'm going to commute AJ with AI here. So I'm going to put the cross. Now I have to put the minus sign here, right? Here I didn't do anything. I didn't commute in this part here, is cross. So it's going to be minus A cross gradient plus F curl of A. So the same thing is going to be minus A cross gradients of F plus F curl of A. That's the chain rule for divergence and curl. There are other identities here that we can look. I mean, for instance, repeated application of nabla, right? We can do it here. We can make just one component, a nabla square, which is the Laplacian operation on a scalar. Let's see here. Quickly, you have time, I think. Let's say the gradient equals to, I'm going to just make one component now. That's one component plus cyclic, right? Permutations. We have a F. Well, I want to make a F AU, FU plus cyclic permutations. But in this case, the U components, I wanna apply the divergent. I want to make the repeated application of gradients of F. So I build a vector which is the gradient of a function, called this F, and calculate the divergence of F. Just the U component FU equals to, as we saw here, right? It's going to be this term here. It's going to be 1 over H1 ddu times F, right? I mean df du. And the divergence of a field equals to 1 over H1, H2, H3, ddu, H2, H3, FU, right? Plus cyclic. Don't have to write the whole thing, right? So if I insert this component here, which is FU right there, so we have the divergence of gradients of F, which is the Laplacian of F. It's going to be 1 over H1, H2, H3, let me, ddu, H2, H3 divided by H1, FU, plus cyclic permutation. That's the general expression. I mean, the nabla operator is something like this. Nabla equals to nabla square. I mean, the Laplacian operator is 1 H1, H2, H3, ddu, H2, H3, F. I mean, sorry. I forgot to put something there. Let me just fix it. Sorry about that. Over H1. I forgot to put here the expression, the final expression, right? FU, I made it wrong, is 1 over H1 dF du. So there is a second derivative here, right? So this is d du plus cyclic permutation. So there are 3 terms, 2 additional ones. So for instance, in rectangular coordinates, so Laplacian equals to our h equals 1. So it's, this equals 1 is d2 dx2 plus d2 dy2 plus d2 dz2. And they have more complex expressions in the other systems, right? As shown in this screen here. Okay, I have that in Cartesian components, in cylindrical. You always have a second derivative term, right? And more complicated one in spherical coordinates. Okay. Also, we have some important properties that we're going to deal with in the course. One is the irrotational field. Okay. I think we have in the assignments how to demonstrate those things. There are ways, there are some suggestions on how to do it. If we have a field that is, obtained from the gradient of another of a function, this field is going to be irrotational. So it has this property. Curl of a vector obtained from the gradient of another one is always 0. So this is called an irrotational field. If you can show that a field is expressed as the gradient of another field, you can show that this field has 0 curl, or in other words, this is one important identity. This is valid whatever is f, okay, independent of f. So curl of the gradient of a function is always equals to 0. We're going to see that the electrostatic field has this property. Is obtained for the gradient of the potential, electric potential, right? Gravitational field has this property. Is obtained for the gradient of the gravitational potential, and so on. Other interesting class of fields are those solenoidal fields. Solenoidal fields are fields that has this property of curling like this, right? So a solenoidal field, on the other hand, is that is obtained from the curl of another vector. So any field that's obtained from the curl of another vector has 0 divergence. Okay. So this identity, curl of, this is wrong here. This is wrong here. Sorry. Let me just fix here. Please fix in the class notes. The divergent of the curl of a field equals to 0, whatever is the field. You can think about those things as observing that you're making the cross product of a vector with nabla. So that would be 0, right? That's what we think, right? I mean, just knowing the property of vector fields, the cross product of a vector with itself equals to 0. So you just look at the identity here, we see that it's nabla cross nabla. So same thing here, right? Nabla dot a vector that is orthogonal to nabla. Even though nabla is not a vector, has expression, is an operator, but I mean, you can think about that to deduce, I mean, to infer that this is going to always be 0 independent of A. So these are solenoidal fields, right? And have those two identities which are very important. The curl of gradient of a function equals 0, and divergence of the rotational of a vector equals to 0. Whatever f, whatever A. Okay? There are some additional identities. We might have to look at those, you know. We might need some of those to do some derivations in our course, you know. We have this property of the mixed product, you know, permutation property. ABC, CAB, if you make a cyclic permutation, you always have the same result. This is a mixed product, you know, a cross product between two vectors, right? This is expansion of a triple vector product, is well known. And there are some more complicated ones, very hard to demonstrate, okay? So we're just going to use those. and so forth. This is going to be very important in dealing with wave equation and with some properties of the fields, magnetic fields and so on. Curl of vector equals gradient of the divergence of the vector minus the Laplacian of a vector. Okay, Laplacian of a vector is not the same as the Laplacian of a function, a scalar function. It's a different thing. In fact, to calculate the Laplacian, you have to use this identity here in many cases. Laplacian of a vector is going to appear when we deal with the vector potential for the magnetic field and the wave equation, Helmholtz equation, in fact. We're going to have that. Well, now I have some three final integral theorems which are going to be very important in the course development. One of them is the Gauss's divergence theorem. We're going to go a little faster on those. I mean, the part that demanded more time for us to lose was the demonstration of those curvilinear systems. Now we have those things already defined. We are going only to generalize the concepts. The divergence theorem, or Gauss's theorem, is the generalization of the definition of the divergence, right? Divergence is like calculating microflux that comes out of a differential volume, right? I pick a differential volume here and determine the microflux. Let's say we calculate the amount of flux that comes out, divide by the volume, right? I have approximately, a very rough approximation, if those things are small, of the divergence of the field, let's say A, right? Let's call F, as we are doing the class notes. So I have a field that permeates space. Then you go on a volume, just calculate the microflux that comes outwards, right? Let's call delta phi, delta psi. Divide by delta V, you have the divergence, let's say, in the middle of the volume, right? So that's the definition. When you make the limit, when this goes to 0, right, you have a differential. You have a differential of a flux by unit volume. Then you can, for instance, calculate how much flux is outwards by knowing the divergence in the middle and multiplying by dV. Right? So that's a definition valid on a differential volume. The question is, what happens if you have a field over a microscopic region? How can I use this definition here to determine a relationship between divergence in a volume which is finite and the surface that surrounds that volume, let's say sigma? Let's say that the element of area out of the surface is the sigma, right? All you have to do is to generalize this concept. So that's what we have here, right? There's a definition on a small volume. So we want to integrate. So you want to pick a volume, and we're going to make small differential volumes and sum all the microfluxes that come out and relate that to the divergence in the center of the volume times the volumes and keep summing those things. So let's say that you have n volumes, okay? So each volume has approximately, roughly, a volume that is approximately V over n. If n is very large, the differential volume is very small. That's what we want to do. We want to know, I mean, when the volume is differential, what's this the sum of those microfluxes, right? We know that according to the definition, this is going to be sums of terms like the volume of the ith volume, the differential volume, times divergence at the center. So when this becomes very small, this becomes the integral on the volume. So that's one side of the equation, right? When you go to calculate the fluxes that come out of the volumes, I mean, for instance, in this red volume here, we have flux coming out that way, this way, this way, that way, and that way. Then you pick up the next volume, right? So in this wall here, there's going to be a cancellation, right? Because one flux is calculated like this. From the next volume, the flux is calculated like that. So they cancel. So now we have a volume that is this total volume here. So the flux is calculated on the surface that encloses these two cells, let's say. As you keep increasing the process, keep adding more cells, more differential volumes, I mean, the integral keeps, the net result is the integral on the outer surrounding surface until you get to the boundary of the volume, right? That's the only wall, the boundary is this outer boundary is the only portion where we don't have a adjoining cell. I mean, here we end, we don't have anything else. So we only have flux outside here. Everything has been cancelled out inside. So the sum of the fluxes results in the flux through the outer surface. So that's what we have as we generalize the definition of the the divergence on a differential volume. If you sum this contribution, have the divergence, which is integral over the volume, right, equals to the flux outwards to the volume, outwards the volume, through the boundary surface. This essentially is Gauss's theorem. It's also called the divergence theorem. You can calculate the flux outward closed surface by calculating the divergence of the field and integrating on the volume, and vice versa, right? You can calculate one or the other. That's the first theorem that's important, right? We're going to have some important consequences of that for our vector fields in electromagnetics. Second important theorem is Stokes' theorem, which relates the microcirculation that comes from the definition, right? We can calculate a microcirculation on a surface that is aligned normal to the direction and can calculate that. So let's call the microcirculation, which is the closed integral of f dl. F is a vector field at play. So the component of the curl along n is the limit, as we mentioned before, of the microcirculation per unit area. This letter L is the microcirculation. I mean, delta L is the microcirculation. As we make a differential area, we're going to have a differential of the circulation per unit area. And this way, you can calculate the microcirculation by doing, delta sigma times n dot product with f. So that's the sigma differential area times dot product with f. So that's a recipe to calculate microcirculation. You calculate at the center of the elements this is wrong here. We forgot. This is wrong. Let's do it right here. Let me just erase here. Please correct the class notes. We have some small typos here. Here is n the sigma times n times curl of f, right? So that's how we do it. So this is the sigma. So this is going to be equals to the sigma dot curl of F. There's a recipe to calculate microcirculation. Calculate the curl of F at the center of the area, multiply by the vector element of the area, which is orthogonal to this vector is orthogonal to the area, dot product, then you have the microcirculation, right? Which is this one here. So now what we have to do is to generalize this concept for a macroscopic area, okay? So what we are going to do is to calculate microcirculations on closed paths that are on a surface. You know, there's one of them. Always doing like this, right? That's the ice elements. This is, it subdivide the surface in n different areas, curved surfaces, small surface. The ice microcirculation is approximately the area element times the curl at the ice cell. Again, this just to have an idea, this is the area divided by n approximately. Then we sum the whole thing, right? We make a sum of all the microcirculations on one side, has to be balanced by the sum of those products, dot products of this thing, and this becomes simply the surface integral on the open area sigma of the sigma dot F. And the question is, what's the sum of the microcirculations? And once again, we have that process, right? We always cancel. I mean, here I do this, right? So I go like this, but on the other one I go like that. So I cancel this thing here. So those two give me a contribution through the outer path. I cancel this one, I'm going to have a contribution through the outer path. And we go along, we keep spreading this thing here, you know. And we keep doing integral on the outer border of these areas. So the last border is the border on the ring, you know. That's the only place where I don't have a neighbor cell. So on one side I have a surface integral of the curl. On the other side I have a closed integral circulation of the field on this border, right? That's what we get. So the sum of all these things cancel on the surface, and the only thing that remains is on the border of the open surface. So that's what we get. This is one side of the equality, and this is the other side of the equality. It's just a circulation using the same property. You go along the path having the surface always on the left, okay? So that's what we get. Circulation of a field can be determined, this is wrong again, it's not the sigma F, this is curl of F. So the surface area of the curl of F equals to the circulation. So circulation is directly connected with the curl of a vector. This is the essence of the Stokes theorem. Okay. There's a second integral theorem that can be demonstrated also as well using that dual definition for the curl. Okay. If you use that other definition in terms of volume, if you recall, I just spoke about that. I can show that we have a similar theorem analogous to Gauss's theorem. Okay? Gauss' theorem is a dot here. The divergence theorem, right? There's a dot here. So we have an analogous theorem for the, here is correct, right? For the curl of F integrated on the volume is equals to the cross product of the sigma with F on the volume, on the surface. that bounds, that surrounds the volume. Okay. Finally, we have this theorem here. Just rewrite here. This is in Portuguese here. Let me just fix here. A is unique. Helmholtz's theorem is very important to the classical electromagnetics theory. It states that given a domain, okay, which we can represent this domain by a volume, a volume V surrounded by a surface sigma. Well, some elements that appear, we have a volume, right? Have the surface. We have the normal outwards, the volume on the surface, and the scalar area element, which is the sigma. What Helmholtz theorem specifies that giving specifications for a vector field. Let's say the vector field equals to A, okay? So if I specify the curl of A, which is, say that is F, and the divergence of A, which is a scalar function F, if this is specified on the whole domain, in addition to the normal components of A on the surface that encloses the volume. So if I know the divergence of A, the curl of A, normal component of A on the boundary, I have a unique field that satisfies these three conditions. There is no second field that has that property, only one. This is very important because Maxwell's equations specify the curl and divergence of the fields, E field, H field, and so on. So, I mean, if you don't specify the normal component, let's say, if you don't say what is the normal component, you might solve differential equations which are going to be known unless of some arbitrary constants. Now, if you impose some boundary conditions on the normal component of the field on the boundary, then you have a unique solution. Because now those undefined constants can be determined because of that boundary condition. But I mean, in essence, even if you don't have the boundary condition, I mean, the general form of the fields can be determined. I mean, how do they depend on the coordinates? You might have, different solutions, but they have the same behavior. The same functional dependence. They might be different in magnitude, in absolute values, but they have a behavior that's known. If you impose a boundary condition, then you have a unique solution. That's essentially Helmholtz theorem. You have to specify divergence and curl, normal component on the boundary, then you have a unique field. Let's make a proof of this. And it's interesting to go to the demonstration quickly here, because we're going to use those two theorems that we just demonstrated, Gauss's and Stokes. So the idea is to build a second vector, B, that has the same properties of A. Same divergence, same curl, right? Because A has a divergence which is F, scalar function F, and A has a curl which is vector field A, F, capital F, okay? And also the second field has the same components, normal component on sigma. So what you do is to build a difference U equals B minus A, and all we have to do is that U is 0 everywhere, okay? So if you, this vector field B minus A has properties. I mean, divergence of the field is divergence of A let's see here, U equals to B minus A, right? So divergence of B equals divergence of A. Nabla is a linear operator, so divergence of U equals 0. Curl of U equals to 0, right? And also the normal component of U on sigma equals to normal component of B minus normal component of B equals 0. So I have a vector U which has a 0 divergence, 0 curl, and 0 normal component on the surface boundary. So this vector has everything to be 0, right? So let's prove it. It could be a constant, but a constant would not be 0. So it's almost proven, right? So just to show you how to prove that he's 0 everywhere, we build the vector U times phi. What is phi? Well, we build, because U is irrotational, we build, I mean, you know that every irrotational field can be obtained from the gradient of a scalar function, right? So U can be written like that because it is irrotational. So we build the vector U equals to the product of U times phi, capital Phi. So you apply Gauss theorem for this field here. Volume integral of the divergence of U phi equals the flux of U phi across the surface. Why do we do that? Because the flux is going to involve the normal component of U on the boundary, which is 0, right? So it's going to be the normal component of U phi, which is the normal component of U, which is 0, so this is going to be 0. So now we have to use the chain rule for divergence of a function times a vector, which we already demonstrated, which is vector dot product of the gradient plus function times divergent. Well, this is U itself, right? Gradient of phi. And divergence of U equals 0. So this term is 0. So this is U square. So then you have integral of U square, magnitude of U square, which is equals to 0. So we prove that the integral of U square on the volume equals 0. And given that U square, right? So we show that dv U square equals 0. There's only one way. This is a positive definite function, right? So the only way, I mean, this doesn't become negative. So there's only way to have a 0 integral of something that is always positive. The only possibility is magnitude of U equals 0. So U itself has to be equals to 0. E equals 0 means B equals to A itself. So there's only one vector that has this property. So that proves Helmholtz theorem. So in essence, these are the properties. Give me the curl and the divergence of a vector field and its component on the surrounding surface on the domain. There is only one vector that satisfies, that has these properties, and only one. Okay. Well, that's all for this class. I mean, with this we conclude our review on vector algebra and some elements of differential geometry. And now we go on next class. We go to start the subject of electrostatics. Until then, bye bye.